Hello, everyone. Today, I'm going to introduce our work, Team Orienteering Coverage Planning with Uncertain Reward. My name is Bo Liu, and this is a joint work with Xuesu Xiao and Peter Stone at the University of Texas at Austin. Our work mainly focuses on finding path plannings for a team of vehicles that can cover as much reward as possible. To motivate our work, we know that many municipalities and large organizations have fleets of vehicles that need to be coordinated for tasks such as garbage collection or infrastructure inspection. We focus on a very common route planning subproblem, and we will use a garbage truck example to describe it. First, vehicles need to continually patrol an area day after day. Some places are required to be visited each day. For example, we want to do some routine check. Other places accumulate costs with unknown rates. For example, the garbage accumulate. The cost is reset to zero once any vehicle visits a place. For instance, the garbage is collected. The overall objective is to minimize the total cost in this area over time. Now we present the problem in more details using some visualization. The overall planning horizon is H. For example, we plan for H days. And then at a particular day, T, the world information is summarized in the graph G with vertices V and edges E. We have a special node V1, which is our base station. All vehicles go out and come back to V1 in a day. And Lij denotes the distance between Vi and Vj. For a particular node Vi, the cost for today is kappa it, which is a random variable with an unknown mean mu I star. The cumulative cost on Vi is Cit, which is just the sum of kappa Ik ever since the last time we visited. The cost on the graph is just the sum cost from all the vertices. Here, the capital T, It, denotes the most recent day prior to T that we visit the vertex Vi. Next, for each vehicle M, the planned route is tau Mt, which is a sequence of nodes starting and ending in V1. Additionally, we might require that the route length is below some threshold L max. And when we visit some node, we will update its capital T. Basically, capital T, I, T plus 1 will become today T if we visit the node Vi. Otherwise, we just copy it from the last time. Now we are ready to present the problem formulation in mathematical language. We call our problem the team orienteering coverage planning under uncertain reward, or Tocpur. The objective is to minimize sum of costs on the graph. And then we have those updated rules and constraints mentioned before. Optionally, we might have a subset of vertices, which we call the must visit vertices. Basically, we have to visit all of them every day. There are some difficulties about Tocpur. First, even when the horizon is just 1, the problem remains NP hard. This can be easily shown by reducing the problem to the traveling salesman problem. Secondly, kappa Ik is a random variable with an unknown mean, so we have to estimate it online. Lastly, even within the same day, we can visit a vertex multiple times. This essentially increases the potential possible plans to infinite. The reason why we want to have this is that because sometimes it is possible for a vehicle to traverse the single place multiple times just to achieve another place faster. Now we introduce some related work. One line of work that is closely related to Tocpur is the team orienteering problem, or TOP. TOP is a multi-tour extension of the orienteering problem, OP, which is heavily studied in the optimization community. In standard OP, an agent plans a path under a fixed length constraint that collects as much reward as possible. Because it is a path, each vertex can only be visited once. There are many variants of TOP. Major ones include the following: stochastic profit OP, SPOP, which considers random profits on each vertex, and OP with time window, or OPTW, which where each vertex can only be visited within a given time window. Then we also have the multi-agent OP and multi-visit TOP. In multi-agent OP, there are two fleets of vehicles that compete against each other. For multi-visit TOP, a vertex needs to be served by multiple agents with different skills in some order. But we want to emphasize again that in all of these variants, a single route cannot visit a vertex twice, which is actually not very practical, because sometimes we want a single vehicle to visit a place twice just to achieve somewhere else faster, as I mentioned before. Another line of work is the coverage planning, CP. CP is the task in robotics of determining a path to cover all points in an area while avoiding obstacles. Unlike CP, Tocpur does not require complete coverage of all vertices. In our formulation, Tocpur primarily focuses on the high-level path planning. As mentioned before, Tocpur is NP hard. So to approximately solve the Tocpur, we propose doing reward estimation and per-iteration planning on the fly. The first step is reward estimation. Because the reward or cost accumulated at each vertex is random, we must estimate the true mean over time. The most straightforward way is doing a maximum likelihood estimation. At day t, all we know about the cost on VI is just the cumulative cost up to the most recent visit to it. For instance, if today is day 10, the most recent day we visit VI is day 3, then all we know is the accumulated cost up to day 3 for VI. Then we just divide that cost by 3 to estimate the true mu I star. And we call this the hat mu IT. Now, given that we have the estimation of the cost on each vertices, we can plan in an online fashion, find the optimal routes for all vehicles at the beginning of each day with the estimated cost. This is essentially a route optimization problem and can be expressed using a mixed integer programming, MIP. But before showing our MIP formulation, we claim a very simple yet important fact. That is, an optimal solution of the Tocpur problem has an equivalent solution where each edge is traversed at most once. This could be best shown using the following figure. So assume otherwise, for example, the edge EIJ is traversed twice by any vehicle. Since the vertex I is visited twice, there has to be another path from J back to I. But if that is the case, we can remove EIJ and reverse the order of the edges along that path. By doing so, we result in visiting the same set of vertices, but in shorter length. Now we are ready to present the MIP. The decision variables are binary decision variables X, Y, and Z. Here, XIJM denotes whether vehicle M will traverse the edge EIJ, and YIM denotes whether vehicle M will visit the vertex I, and ZI denotes whether vertex I will be covered by any vehicle. The complete MIP formulation is like the following. I will explain them in details step by step. First, the objective is we want to maximize the cumulative cost that we can cover by the current planning. And in order to do that, we just multiply the cumulative cost C by the random variable Z. Z denotes whether we visit a vertex VI. Then we have the constraint 4, which ensures each route starts and ends in V1. Constraint 5 ensures that there's no self-loop. Constraint 6 and 7 ensures the definitions are consistent. Basically, the definition of X, Y, and Z, they are consistent. Constraint 8 ensures the flow consistency. The amount of outflow should be equal to the amount of inflow for every vertex. Constraint 9 ensures the route length constraint. And most importantly, constraint 10 to 12, which are novel, they ensure the planned routes are always a single connected component. In other words, without constraint 10 to 12, the following plan for a single vehicle is possible. Basically, the algorithm can find two disconnected components, which definitely a single vehicle cannot achieve. The entire algorithm is summarized in the following algorithm box. Basically, on each day, we first calculate the cumulative cost estimation. And then we solve the above MIP using those estimations. And when we visit some vertices, we will update our estimation. Now we present some empirical results. We denote our method as the TOCP method, and we compare against the baseline methods that view Tocpur as the TOP problem. Here we abuse the notation a little bit and just called it the TOP method. Additionally, we introduce a greedy method with heuristics as another baseline. The greedy method plans routes one by one and step by step. At any step, the greedy method looks for the vertex with the best cost over distance ratio if it is reachable and goes to that vertex. We simulate 600 random generated graphs with a varying number of vertices. On the left, we show the comparison among TOCP, TOP, and the greedy algorithm on 600 graphs. Because we limit the computation budget to 1,000 seconds, so it is possible that TOP and TOCP might not be able to find the feasible solution within that time limit. On the last row, we show the number of failures in that case. As we can see, TOP actually fail a lot. TOCP occasionally fails, but the number of failures is much smaller than the number of failures in TOP. On the top two rows, we show the average cost and the average computation time for all algorithms on a subset of 120 subgraphs where all algorithms can find a feasible solution. As we can see, TOCP always achieve the minimum average cost. On the right, in table 1, we do independent samples t-test for TOP versus TOCP and the greedy method versus TOCP. Basically, we show that TOCP outperforms the baselines significantly in most of the scenarios. Here, we provide an example run of the one iteration planning of TOCP for 3 vehicles. The graph is provided on the left, where the red vertices are the must-visit vertices. The yellow vertices are the optionally visited vertices. On the right, we show the resulting plan. As we can see, TOCP finds the optimal plan, which clears out all the cost on the graph. We also provide a video showing, basically here's the physical demo of our algorithm on 3 physical robots, and we do the plans on the UT campus. Regarding the future directions, we summarize potential future directions in below. First, we can design approximation algorithm faster than TOCP, but better in performance than the greedy algorithm. We can also investigate theoretical guarantees of TOCP per iteration planning. For example, what is the regret bound for this algorithm? Lastly, we can also incorporate low-level controls along with the high-level plans for Tocpur. Thank you very much for your listening, and we provide the QR code to our paper and the video in below.